Okay, so collision model is really simple. We know that molecules need to collide, need to come together to react, but not all collisions guarantee that a reaction will occur. In fact, only a very small portion of collisions produce a reaction. This is because molecules have to collide with enough energy and they have to be properly oriented. So I did this diagram. Sorry for my diagrams. I did them in Google Drawings, and well, this is okay, but the other ones are are awful. But well, Nemo. Okay. So for example, in this reaction with carbon monoxide and nitrogen dioxide, this is showing the energy of collision. If they come together with enough energy and in the proper alignment, then the products will be formed. But if they are properly aligned, but with not enough energy, no reaction will be formed. Or maybe they do have the energy, but they're not aligned properly. So there's not going to be a reaction because here the carbon is getting together with the nitrogen, and we don't need that for the product. So that's the collision model, as simple as that. Any questions? No, right? It's super simple. Okay, the activation energy is the energy needed for the minimum amount of energy to initiate a reaction. This is the activation energy. And in this graph, what I try to show is that the reactants, A and B, need to overcome a certain energy, and that's the activation energy to make the products. You have activation energy in both cases. If you have an exothermic reaction, remember that energy is released. So that's why you end up in a lower potential energy as you started. Or you can have also an endothermic reaction where the products are on a higher energy level than the reactants. But still, the reactants have to overcome this bump that is called the activation energy. Okay, a catalyst will lower this activation energy. A catalyst is a substance that speeds up a reaction without being consumed. It's not considered neither a reactant nor a product. Well, it is considered a reactant, but you will recover it. It won't be used up. And the activation energy, I'll show it here in red, the activation energy will be lower with a catalyst. Okay, now we're going to see reaction mechanisms and how they affect the rate law. Okay, last session, we did a lot of examples with rate law where the equation was given, the reaction was given, and to be able to do the rate law, we did two cases. We did the case where initial rates, where we had experimental data of several experiments that started at different concentration, and we check if the concentration was double while the rate was double, then it was rate 1 and so on. Or we could have the rate laws from the graphs. Do you remember the graphs that we saw last week? Which graph was for order 1? Do you remember the straight line was shown with the graph of time versus natural logarithm, correct? So exactly, natural log. So if the other way to determine the rate law was with only one experiment and observing how the concentrations change during time, and then graphing those data to check the rate law. Okay, now we are going to do another way to determine the rate law with the reaction mechanisms. So for example, for this reaction, this is the rate law that will be that was determined from experiment. Now, from this reaction, this reaction mechanism was proposed. So the reaction mechanisms is a set of steps that give the overall reaction. Let's check all the contents of this reaction mechanism. For example, you notice that NO3 is formed on the first step, and then it is consumed on the second step. NO3 in this case is called an intermediate, a species that is neither a reactant nor a product from the overall reaction, because it is formed and consumed during the reaction sequence. We also can tell from the reaction mechanism that these steps are called elementary steps, a reaction whose rate law can be written from its molecularity. And molecularity is defined as the number of species that must collide to produce the reaction indicated by that step. Let's see some examples. So for example, we could have an elementary step that is unimolecular when we only have one reactant. So then the rate, what it meant by the rate can be taken by this molecularity, is that you do only the rate of the reactant to the power of the coefficient. So in this case, the rate will be K times the concentration of A. We can have elementary steps that have a bimolecular molecularity, in which we have two reactants. It could be the same reactant, but in a double ratio. And then the rate will be the K times the concentration of A to the power of 2, because this one will end up with coefficient 2. And so on with bimolecular with two different reactants, this will be the rate law, K times the concentration of A and B, and so on. If the molecularity is thermolecular, then the rate, we can take it directly from the ratios of the reactant. Okay, let's go back to our reaction mechanism. The reaction mechanism is this one. So now, by its molecularity, we know that the rate law of the first step will be K times the concentration of NO2 to the power of 2. And then of the second one will be K times the concentration of NO3, the reactants, times the concentration of CO. Any questions on how to get the rate of the elementary steps? So now, the multi-step reactions often have a step that is slower than the other steps. Now the rate will depend on that slowest step. That will be called the rate determining step. And this is the steady state approximation that you asked. I don't remember who asked this, Perla or Anika? You asked this last week. So this is the concept of the steady state approximation. And you can think of it that like if you're in I don't know, if you are in your car and there's a lot of traffic, maybe the traffic is because in one step, in one road, there's a blockage or somehow. So you cannot go, you won't be as fast as the cars that pass that slowest step. So since the overall reaction cannot be faster than the slowest step, we assume we make an approximation of the steady state, the approximation of the slowest step, and we consider the overall rate to be the same as the rate of the slowest step. In this case, the first reaction. So that's how we can say that the overall rate, it's equal to K times the concentration of NO2 to the power of 2. Any questions? Okay, we're going to start with an example. No, sorry, not yet. Okay. One thing to consider is that reaction mechanisms are theoretical. We cannot be sure, absolutely sure about reaction mechanism. Reaction mechanism can never be proved Absolutely. Why? Because we don't have a zoom-in vision to see what is actually occurring on a chemical reaction. We can just assume and make predictions. So for a valid scientific reaction mechanism must satisfy two requirements. The first one is that the sum of the elementary steps must give, the addition must give you the overall balanced equation, and that the mechanism must agree with the experimentally determined rate law. So let's check if the two requirements are met for the reaction that we were talking about. So if you have this reaction mechanism and you add them, you add both reactants, like all the reactants, you place them on one side, and you add all the products, and then like in math, you cancel the substances that are on both sides of the equation, you get the overall reaction. So with this, we prove that the first requirement is met with this. The second requirement is that the mechanism must agree with the experimental determined rate law. So we already talked about that the rate law is the one determined by the slowest step. And if we go back to the original slide where we have the problem, it does match the experimental rate because this is the one that was given by experiment. So this reaction mechanism does meet the two requirements. Now, this is something very important. We can only say that this proposed mechanism may be the correct one, but we will never know for sure. So how do chemists propose a mechanism? So what chemists do to propose mechanism is that first they determine the rate law with experimental values. That's the first step. And then with intuition and knowledge, previous knowledge, the chemist constructs possible mechanisms. And then that chemist, or asking for help from the professional community, with further experiments, the chemist or the group of chemists try to eliminate the mechanisms that are least likely to occur, and that's a proposed mechanism. But again, this is only in theory. So an accepted mechanism is one that satisfies the two requirements. Okay. Now, this is where I will explain the multi-step reaction energy profile. Sorry for my diagrams. I couldn't get the curved line to be like all in one step, but well, the important is the idea. Now, in the multi-step reaction is that we are going to have two bumps to show the two steps on the equation. So now, since the first one is the slow step, that's why it will have the activation energy will depend on the slowest step. The activation energy will be the one with the slowest step, and that will be the highest bump. So the first reactants are NO2 and NO2, will go here, and then the transition state, and then the intermediate will start again with NO3 and CO here, and will again go to another bump, to another transition state, until they produce the products. The enthalpy or the change of energy is from the initial to the final, and the activation energy is from the initial to the highest bump. Okay, Perla, you're asking, would a catalyst affect a transition state and intermediate? Okay, a catalyst will affect the activation energy. So if you have a catalyst, this bump will be lower in height. That's how a catalyst can affect. So a catalyst will usually affect one of the steps, and for it to be a useful catalyst, it will affect the slowest step, and it will lower the bump. And that's it. So it will lower the overall activation energy, which will be determined by the slowest step. Okay? Okay, let's move. So now we have an example with a different reaction. For this reaction, the intermediate won't be affected. No, the intermediate would end up being in the same level of potential energy. The catalyst will only make the bump a little bit lower. So the reaction will proceed more like easier with less energy. Okay, so this example, 2 moles of nitrogen dioxide and fluoride gas produce this product, NO2F, and they give us the experimental rate law, and it's known to be this one. A proposed mechanism is with 2 steps, and they're asking us for the intermediate, and if this is a proposed, if this is a valid proposed mechanism. So letter A, what is the intermediate in this mechanism? Excellent. F is the intermediate. Very good. How do you know? Because it's not on the overall reaction. It is formed on the first step, and then it's consumed on the second step. So that's why it is considered an intermediate. Okay, and now let's move on to letter B. What do we need to do to check if it's an acceptable mechanism? It needs to pass the 2 requirements. Do you remember what were the 2 requirements? Yes, you add the steps, and the steps have to give the overall reaction. That's the first one. And what is the second requirement? Exactly. See if the rate law matches the experimental rate. So let's check the first requirement. So we add the 2 equations, and we do get the overall. So the first requirement is met. And then remember that the overall rate will be the rate of the slowest step according to its molecularity. So it would be the concentration of NO2 times the concentration of F2, which is actually the experimental rate. So the second requirement, it's also met. So is this mechanism valid? Yes. Does it mean that it is the correct one? We don't know. Questions? Okay, let's move on to another example, a little bit more difficult. In this example, we have, again, I don't know why I chose reactions with nitrogen, but well. Okay, now we have nitrogen monoxide and oxygen that produce nitrogen dioxide. Again, they gave us the experiment, the rate law obtained by experiment. And now the proposed mechanism is the following. Notice that in this proposed mechanism, we have an equilibrium reaction. We have one that goes, it has a rate for the forward reaction and a rate for the reverse reaction, well, a K value. And we have the lowest step below. So again, they're asking if this mechanism is valid. So let's do the first requirement. And if we add the 2 equations, we will get the overall. So the first requirement is met. Now it's a little bit tricky to get the rate law. Why? Because the slowest step has an intermediate. So now what we need to do is figure out a way to substitute that intermediate in the rate law. And this is how it's done. Notice how N2O2 is formed on the first step, right? And since this reaction is an equilibrium, we can assume that both rates of the forward and the reverse reaction are equal. So that's how we can assume that K1 times the concentration of nitrogen monoxide to the power of 2, it's equal to the reverse, to the rate of the reverse, K minus 1 times the concentration of N2O2. From here, what we do is we solve for N2O2. We solve for N2O2, so we pass this K minus 1 dividing, and we will have this rate law. And then what we can do, since the K's are constant, we can place them together and have the rate law of K times the concentration of NO to the power of 2, where K would be these two constants. Is it understood what I did here for solving for N2O2? So now the next step is to substitute N2O2 on the slowest step. So now N2O2 we substitute with what we had before, and we will get this. We had before, and then we have again 2 K's, but it doesn't matter because since K is a constant, we can place them together as a new constant. So now the rate would be K times the concentration of NO to the power of 2 times the concentration of O, and it matches the experimental rate law. So we are proving we are the second requirement is met. So this is a valid reaction mechanism. I wanted to show you again a multi-step energy profile, because now in this case, since the second reaction is the slowest, now the bump will be higher on the second step. And now the activation energy will be determined by the height of that energy. Notice how the activation energy now will be dependent on this one, since that's the lowest rate. Okay, now we have another example. So this is the reaction. Again, nitrogen dioxide and carbon monoxide gives you nitrogen monoxide and carbon dioxide. It says, state the rate law for the following equation and for the following proposed mechanism. Okay, is the first requirement met? If you add both of the equations, would it give you the overall? Yes, right? If we add them, it will actually give you the overall. Which is considered the intermediate in this reaction, in this mechanism? Excellent. NO3 is the intermediate. How do we know? We know because it's not on the overall, and it is formed on the first step and consumed on the second one. Correct. So, and we also have to remember that the slow step determines the rate law. This is the slow step, right? So we need to, the problem is that the slow step has an intermediate. So we need to use the other reaction to figure a way to substitute for NO3. Okay, so that's the rate for the slowest step. The K of the concentration of NO3 times the concentration of CO. As we mentioned, it's an intermediate. So we get we equal the rates of the first reaction. Since it's at equilibrium, we can say that the forward rate it's equal to the reverse. So now we can substitute for NO3, and now I just omitted the case since at the end is the same since it's a constant. So I'm just going to divide past this one dividing. And now I can substitute NO3 in the rate of the slowest step. And that's how I will get this rate.